Okay, I don't usually make YouTube videos or any type of social media promotional content, but I've been messing a lot with the GJK algorithm lately because I'm writing my own time of impact physics engine. And there's almost no video on YouTube that shows really in a good way how the algorithm works. And of those, there's maybe one by Casey. And even that one does not show both GJK algorithms. There are actually two GJK algorithms that serve kind of different purposes. The only kind of algorithm you can really find on YouTube or GitHub is what I call the shortcut GJK algorithm. And it's probably technically faster, but it returns less data than what I call the complete GJK algorithm, which returns more data. So I'm going to try to show both algorithms and why you would want to use one or the other. So before I start, though, I want to kind of explain what the GJK algorithm is. It is a very simple, very fast algorithm to determine intersection between two shapes in 3D, or two convex shapes in 3D, or two convex shapes in 2D. And the way the algorithm works is based on Minkowski differences or Minkowski sums. So if you have this shape 2 right here, and you have this shape 1 right here, you would take every single vertex in shape 2 and subtract it by every single vertex in shape 1. So that's an n squared operation. So if each of these shapes has 100 vertices, your point cloud, this right here is the Minkowski difference. This has 10,000 vertices, okay? And the reason the algorithm is so efficient is because you don't have to check all of these vertices. You can abuse a property of the Minkowski sum or Minkowski difference to only check an extremely small subset of them. And I'll show that later. And so the way it works is, you can imagine if I take these two shapes and I align them so that this vertex is like basically overlapping, right? Which that's close enough. If you subtract these two vertices from each other, shape 2 minus shape 1, you'll end up with approximately 0, like 0, 0, 0, the origin, which is right there. And you can see that's the red vertex. It's basically 0, 0, 0. And if I move it closer, the point cloud moves further into 0, 0, 0. And so the logic of the GJK algorithm is, if the shapes are overlapping, there will be a tetrahedron, like a triangular pyramid, the most simple 3D shape, that will contain the origin. And so with the GJK algorithm, you operate on a simplex, which is just a simple shape. You operate on a simplex and iteratively update the simplex to try to enclose the origin in your tetrahedron, which might sound complicated, but it's not. So I'm going to show, let me first show how the algorithm works, right? Let me show the code. So to start with, I create my simplex. It has a single vertex. Here I'm assigning my single vertex. The way you get the simplex, the way you get the support point, the vertex, right, of the simplex, is you subtract the most extreme point on your second shape by the most extreme point in the opposite direction on your first shape. You have to choose a starting direction, and for this algorithm, it does not matter. It does affect the efficiency of the algorithm, so you want to start with a good guess, which is the first shape minus the second shape. That's the starting direction. It affects the efficiency of the algorithm, but you will converge on the correct result no matter what. So I want to show this support function because this is one of the various things that makes the GJK algorithm so good. The support function, all it does is you have your vertices of your first shape and you have a direction. And all it does is it returns the vertex of the shape, the most extremal vertex of the shape in this direction, which is just a dot product. Because the dot product is showing basically, I guess, like how aligned the directions are. So you just dot every single vertex in the shape with a direction and return whichever vertex gives you the largest dot product, which is all this code is doing. So now at this point, we have the most extreme vertex on shape 2 in this direction and the most extreme vertex on shape 1 in the opposite direction. That is our first support point. So if we look here, that is this red point. This is vertex A of the simplex. If I step the algorithm once, you can see it drew a line going back this way. What it's doing now is now I'm updating the direction to go from 0, 0, 0 to simplex vertex A. So what it's trying to do is find a direction going to 0, 0, 0 from this red point. I went back a step. So that is basically to my left. And so it's trying to find whichever point in this point cloud is most maximally to the left, which if I go forward again, there I found it. It's this red vertex. So now that I updated this direction, right, to negative simplex A, now we start the loop. Using that direction, I basically add that support point, the most maximal point in the point cloud, which is this function again, in that direction to simplex A. And so before that, simplex A, one of the properties that allows you to make this algorithm more efficient is that you always want simplex A to be the most recently updated vertex. So I basically shift everything in the simplex back. This is how I chose to do it. So A becomes B, B becomes C, C becomes D. And then I update simplex A to the new support point, which is this red point right here. So now if I step again, now it's trying to find, this is a little bit confusing. Let me adjust this. There we go. It's trying to find something in the direction from this line to the origin. And so the way this works is now it went into, this is like the root of the logic. This is like the main logic of the entire algorithm. For the simplex, it has three potential cases. It can be a line, it can be a triangle, it can be a tetrahedron. These are the number of vertices. And so this one is a line. So we jump into solve simplex 2. There are only two cases for a line. The origin can either fall on the line. We're projecting the origin onto the line. The origin can either fall on the line, or the origin can be closest to the new vertex. One of the optimization tricks with this algorithm is the origin can never be closest to vertex B because that was the previous vertex we updated from. If you want to learn more about the exact implementation of this algorithm, you can watch Casey's video that I'll put in the description. He describes all of this in a lot more detail than I'm going to. But so basically, we just check if the origin falls on the line, we update from the projected point of the origin on the line to the direction of the origin, which is, in this case, basically straight up. So now it's trying to find a new support point in this point cloud that is straight up. And here it found it, right there. So if I update again, it updated its new support point to be straight up. And again, kind of complicated. Let me scoot it over. There we go. Okay, good enough. So now it updated support point to be straight up. So now what it's trying to do, now we loop again. Here it went back here, shifted everything, updated. This is a new support point, straight up. Now we go back into the main loop. Ignore all of the debug stuff. Now we go back into the main loop and we're on case 3, a triangle. This one is probably the most complicated case actually. And so what happens is, again, I'm not going to go into all this logic. Casey's video does a good job of that. But basically, I'm trying to determine if the origin, which is very close to the triangle now, is closest to one of these vertices, closest to one of these lines, or closest to the triangle. And that's what all of this logic does. All of this. And so in this case, just looking at it visually, it looks like it is closest to the triangle. So I update one more time. So now it's projected from the origin onto the triangle and in the direction of the origin, which is the normal of the triangle. So it's trying to find a support point most maximally in the normal of the triangle, which is straight to my left. And look, it did that. So there it goes. That's the new support point, and it has created a tetrahedron. And now this tetrahedron encloses the origin, as you can see, right there. And so if I press next one more time, the algorithm is done. And it says yes at the top, which means these two shapes do in fact intersect. And so that's all there is to the, well, there's one more step that this specific scenario did not touch. Let me cover that. The last remaining step is when it is a tetrahedron, but it's not yet colliding, which, yeah, if it is a tetrahedron, what it does is it gets all three planes. And I want to point out, where is it? You don't have to check this face, because the same logic with why we only had to check one point on the line, we know it cannot possibly be this face because this is the face that is furthest away from vertex A, the red vertex of the simplex. That's one of the optimization tricks of GJK. But in the tetrahedron case, all you have to do with the shortcut version, at least, is check if it's in the direction of triangle ABC, ACD, or ADB. And whichever triangle it is in the direction of, which can be more than one, you update the simplex to that triangle, and then you pass it into the solve simplex function. If the origin is in the direction of any of these three triangles, you know that the tetrahedron does not enclose the origin, because otherwise it would not be in the direction of any of the three triangle normals. So you return false, which means it is not intersecting, and you convert the simplex back to a triangle and pass it back into the solve triangle function. Otherwise, you'd have to rewrite all this code 3 times. So if it is not in the direction of any of the three triangles, you know that the tetrahedron does enclose the origin, so you pass back true. And what's happening is, when it collides, the algorithm ends. It just returns true. So that's basically how you do the main logical chunk of the algorithm. The exit condition for this algorithm, specifically for the shortcut method, is this right here. And this is after you find a new support point in the point cloud. What it's saying is, if the support point you found is not in the direction of the origin, it cannot possibly be intersecting the origin. The two polygons cannot possibly be intersecting. And the logic is because the way this algorithm works is it constantly jumps around the origin. If I go back, it started here, jumped past the origin, started here, below the origin, jumped past the origin, started here to the right of the origin, jumped past the origin. So if it ever doesn't do that, you exit. A lot of people whose code is not correct, or maybe they just want to be sure their game doesn't freeze, they actually just say something like, they just loop like 64 times. And that's it. And it'll always solve it, within 64 times or whatever, if you're not doing something crazy. But that shouldn't be necessary. This algorithm converges very quickly, and if there's nothing wrong with your algorithm and there's nothing wrong with your shapes, it should never freeze. But anyways, that's the exit condition for the algorithm, and that's basically it. So now I'm going to explain the other GJK algorithm. This algorithm you can basically not find any information about online. I found one presentation by Aaron Cato, the creator of Box2D. I found one presentation he did where he roughly described this algorithm, and I found a resource he pointed to, which is a very good textbook that I'll also link in the description. That resource explains how this part of the algorithm works. So this is the complete GJK algorithm. So I'm switching to that. So you can see up here, I switched to the complete GJK algorithm. So these two shapes intersect, and it'll do the same thing, I think. It'll do the exact same stuff if they're intersecting. Yes, they're intersecting. It took the same amount of steps. The trick with the complete version of the algorithm is that if they are not intersecting, you can see these red points right here. These are the closest features of the convex shapes. And so I'm going to make it a little bit more complicated if I can. Yeah, this is good enough. So let me move this one down. Here we go. Okay. So what this algorithm does, it's almost the same. This is this version of the algorithm. The purpose of this algorithm is that upon non-intersection, the algorithm does not exit. So I have a specific check in here down below. If I don't want it to resolve completely, which I usually don't, otherwise I would use the shortcut algorithm, I don't do this dot product check. And so the purpose of this algorithm is upon non-intersection, it continues until it finds how do I word this? The algorithm continues until the projected point of the origin onto the simplex is the most maximal in the direction of the origin as it can be. So I'm just going to show you what happens here. And this algorithm works with projection. The simple GJK algorithm works, as you saw, by iteratively updating the simplex based on the nearest feature of the simplex to the origin. So it just iteratively tries to get closer and closer to the origin. The complete version of the GJK algorithm actually projects the origin onto the simplex. It projects the origin onto the simplex, which is this P here that is returned for each function. And then it reduces the simplex down to the most minimal simplex that is supported by the projected point. Okay, so that probably sounds complicated. Here's what it does. Let me step through this. So it starts off with that red point. It's trying to get the point most maximally in the direction of the origin, which is that. It created this line. It projected the origin onto the line, which you can see is this white cube. So that is the projected origin. And actually, it is done. Okay, so that technically that's correct. That was very fast. So what's happening is this is the projected point of the origin onto the line, and then it tried to get a new support point in the direction of the origin, and it found it. It was probably either this red point or this green point, and it checked. This is the check. Where is the check? Where is the check to exit the algorithm? This. If the dot product of P, the projected point and the direction, is greater than or equal to the dot product of the support point and the direction with an epsilon buffer. So if this is the case, basically it knows there is no longer a point more maximally in the direction of the origin than it has already found with this projection, which means it has found one of the nearest possible shapes on this object to the origin, which is true. If we look over here, it's decided these are the two nearest shapes, okay? And if I continue one more time, it's decided these are the two nearest points on the 3D shapes to each other. So I can keep doing this algorithm. And here, I found these two faces are the nearest shapes, and these 2 points are the nearest points to each other. And all of this is, at least, looks like very correct information. You can see as the things move around, and I have to continue more times for this one. You can see as everything moves. Very nice. Following the triangles, which makes sense given the shapes. And so that's basically how this one works. Projects the origin onto the current simplex. I want to show a more complicated case. Maybe here. God, I don't even know how. Maybe here. There we go. Projects the origin. Let me restart. So it makes this line again, which makes sense. Projects the origin onto the line, and then finds something in that direction most maximally, which is this triangle. Now it's trying to get to the origin, so this line is going to be what is closest to the origin. So it's going to project the origin onto that line. There it is, and that is the most minimal simplex supported by the origin. So it just breaks the simplex down to that line, and then once again updates in the direction of the origin, and it has this face. Now this triangle is actually the most minimal simplex shape supported by the origin, which is projected onto that triangle, as you see. So when I update again, it makes a tetrahedron, and so on and so on. And I keep updating, it keeps getting the minimal face. The face actually updated there. Again, face updated, there's my line, and that's it, algorithm done. So this code is more complicated, and it does basically the same thing. But here is the difference, right? You get your direction. You have to keep track of the support point on each convex shape in order to return the closest features at the end of the algorithm. So you keep track of the support point, and you keep track of the support point in the simplex, the actual point cloud support point. And so you continue on, and here you do the same kind of check. I have a single case for a single point, and I just return the projected origin onto the simplex is simplex A. That is the only point on the simplex. And for case 2, it is a line. So the difference is this algorithm is modifying the simplex and returning the projected point onto it. So if the origin falls onto the line, we project the origin onto the line and return it, which this is line projection code. And based on this, we can shortcut. We already know that the origin falls onto the line, so we don't have to do like the normal thing here, right? Which is like this. This is normally what you would say. Something like that. Yeah, whatever. That kind of thing. You don't have to do that. So if the origin is closest to A, you just update the simplex back to a single point and return the single point. Very simple. For the 3D shape, you do basically all the same stuff as in the Casey version of the algorithm, which is the shortcut version of the algorithm. You're checking if the origin is nearest to the line AC. You update B to BC. So now you have line AC as your simplex, and you update the simplex count to be 2. So now you just have a simplex line of A, and then B is C, so AC. And you also do projection stuff to get simplex A plus the percent through AC times the vector AC. So this code is, again, just projecting the origin point onto the line. That's it. And this continues through all of the various cases, which is what Casey outlined in his video, if you want to see this in more depth, like why this is. And it just does the same math, projecting everything onto the lines and points. Down here, this is math to project the origin onto the triangle. In these cases, we know the origin falls onto the face of the triangle ABC, or onto the face of the triangle ACB. So we project the origin onto the triangle. In Casey's video, he mentions something like, in a lot of academic papers, he sees this algorithm with divides, and he doesn't know why there's divides. There are no divides in this algorithm. And that is true for the shortcut, faster version of the algorithm. With the more complicated version of the algorithm, there are divides because you have to project the point. And this algorithm has, the complete version of the GJK algorithm has 2 main benefits. Before I get into that, I mean, there is one more case again, the tetrahedron. The tetrahedron for the complete version of the algorithm is actually more complicated. The tetrahedron, with the Casey video, you only have to check if the origin is in the same direction of any of these 3 faces and pass it back down to those faces, like those triangular faces, right? In this version, you have to check every possible combination because you have to get the nearest point of the origin on the tetrahedron and project it. So there could be 2 faces that the origin is in the same direction of, or even maybe 3. Could it be 3? Well, whatever. You have to check all of those potential cases. And so that's effectively what I'm doing here. If it is not in the same direction of any of the faces, the origin is inside the simplex, right? That's the first check. That makes sense. If the origin is only in the direction of one of the faces, then I update the simplex to be that triangle, and I pass it back into the solve simplex 3 function. Here I'm returning the projected point of the origin onto the specific triangle that I just constructed. So here I'm constructing triangle ABC, here I'm constructing triangle ACD, and here I'm constructing triangle ADB. And that is basically all that you do there. It becomes more complicated when the origin falls on multiple triangles. So what I am doing here is basically I'm trying to check the distance from the origin to all 3 triangles. This is the catch-all case here, basically. And now I know it falls on at least 2 or more triangles. So I'm creating 3 new simplexes. There may be a better way to do this, but it doesn't really matter. It's very fast. I'm creating 3 new simplexes, ABC, ACD, ADB, which are the 3 triangles constructed. I solve all of them, which kind of sucks. But yeah, solve all of them, get the distance squared to the projected point on all 3 triangles, and I check whichever one is smallest. I update the main simplex. This is JAI syntax to update a pointer. I'm updating the main simplex to one of those 3 triangles, and then I return the result of the original projection math onto that triangle. So I don't know if this is confusing or not, but I'll go over it again. Essentially, if it's not outside any face, it's within the tetrahedron. If it's outside a single face, you project it onto that face triangle. If it's outside multiple faces, you have to check which face the projected point is closest to. You can't assume anything like you do in the other algorithm. So you have to check which face the projected point is closest to and return that projected point. So again, at the result of this, all this algorithm gives you back is P, the projected point. So one of the main benefits that I was going to get into of this algorithm is it just tests if this projected point P is within epsilon to the origin. So you could potentially intersect with a single vertex with this algorithm, a line, or a triangle, whereas the other algorithm can only return true, if you see here, upon the tetrahedron case. This is the only way the algorithm can return true. So this one can intersect with any of the 4 potential shapes, or 3 potential shapes. This one can only intersect it can intersect with any of the 4 potential shapes. And that's one of the benefits, is using that data then, you can get back upon non-intersection. At this point, you know when this thing ends, which is when it's most maximally in the direction of the origin. That's the main exit condition here. When P is most maximally in the direction of the origin, it cannot find a better support point. The algorithm ends. It gives you back a simplex. And on this simplex, this whole time, we've been keeping track, remember, of A1, A2, and all that, which is the support point on the individual shapes. So in this algorithm, when it ends, you can look back at A1, A2, B1, B2, C1, C2, D1, D2, and find the actual support points on the individual shapes. That information will give you the closest features on the shapes. And now you can do 2 more things with that information. Given that information, you have your projected point P at the end of this algorithm upon non-intersection specifically. You have your projected point P. The distance from this projected point P to the origin is the distance between the 2 shapes. It is the smallest possible distance between the 2 shapes. That's another bit of information you can get back. So if I look here, this algorithm is finished. This white spot right here is the projected point P. The distance from that white cube to the origin is the same as the distance between these 2 pink points right here. And then the last bit of information you can get back from this version of the algorithm is these 2 pink points. And so these pink points are the actual closest points, closest individual points between the 2 shapes. And the way you do this is slightly more complicated. I have a method for it here. You are getting the local points of the simplex for the projection, right? And so what you do is you convert it to barycentric coordinates. Barycentric coordinates are effectively coordinates that are relative to a given shape. So barycentric coordinates on a triangle, x, y, and z will go between 0 and 1 depending on where the point is relatively inside the triangle, right? So it's just a coordinate system relative to a specific shape. So what I'm doing here is I'm converting the projected point P. This is in the case of a line. Like in the case of a vertex, it's obvious, right? In the case of a vertex, the closest points are A1 and A2. For case 2, the barycentric coordinates on the simplex, I'm converting the projected point P into barycentric coordinates for the line A and B. The math for that is, for the line case specifically in the math, it's pretty simple. You're getting like the delta vector between B and A, delta vector between P and A, the dot product of those divided by the dot product of AB. This is the same math as projecting a point onto a line. And I return T. The barycentric coordinate of a line is a number, kind of. So that's all information I need. And so in case 2 for a line, I get the barycentric coordinate, which is a float of the line AB. And now I pass that barycentric coordinate back into this convert Cartesian coordinate for simplex A1, B1, and simplex A2, B2. So this is converting this barycentric coordinate from the reference point of line AB into the reference point of line A1, B1, and into the reference point of line A2, B2. And those are the coordinates I return. And this is the convert Cartesian coordinate for the line. It's also very simple. As you can see, it's just getting the length along a line vector. That length is the barycentric coordinate. For the triangle case, it's the same logic, but slightly more complicated because it's a triangle. I'm converting the projected point into barycentric coordinates for the triangle ABC. That is also basically just the projection math of a triangle. This is what that is for a triangle. It's basically treating point P as like a tetrahedron kind of thing, and then creating a result where x, y, z go between 0 and 1 for the given coordinates again. And then to convert your triangle back into Cartesian coordinates, I pass in the same vectors ABC and my barycentric coordinate, and it's this. It's AX, BX, CX with barycentric X, Y, Z. So it kind of makes sense too. So in the triangle case, I'm doing the same thing. I get the barycentric coordinate of the projected point onto ABC and convert it into the Cartesian coordinate of the barycentric value onto A1, B1, C1, and A2, B2, C2. And that gives me back my local points that are the closest points possible for the two convex 3D shapes. And that is basically this algorithm. By doing this check right here, this is very important. This check, because what will happen if you try to return this data for the shortcut version of the algorithm is there is a good chance it will find another support point in the point cloud that is the same extremal value, and it will keep trying to update, and it will go on forever. However, because you never have the projected point in the other version, now that you have the projected point onto the simplex, you can compare that projected point with your newly found support point, and you can check whether or not that support point provides any value to updating the simplex or not. And if it does not, that is this case where you have found the nearest features on each shape, and you can return that. So that's basically the value of the complete version of the GJK algorithm. This information can be used in a lot of things. And the reason I need this is I'm writing a time of impact physics engine, and I need to know the closest features on the two given shapes. One final thing that I want to also discuss is that, also, I guess I could show a cube. You can see kind of how, there's not as many coordinates. This sphere is being updated to every vertex of the cube, which is pretty visually obvious here and nice. Yep, and that's the closest points between the cube and the sphere. Makes sense. Makes sense. So one of the benefits also of GJK algorithm is I am updating my vertices before I pass this into the GJK algorithm, but you don't have to update your vertices. So what I mean is, as I rotate, before I pass the vertices into here, I actually update all the vertices. But because the GJK algorithm operates on a support point, all you have to do is in this support point, you can modify the direction, right? So if I have my transformation matrix, transform, I'm not actually going to do it here, but if I have my transformation matrix already initialized, all you have to do is new direction is a vector 4 of your old direction, something like this. Transform times this dot xyz, or I'll keep it like this, yeah. This is your new direction with the rotation, something like that, right? But actually it'd be like, you have to get xyz. This is a 4-dimensional vector. So you don't actually have to rotate your vertices before you pass them in. You can rotate the direction that you want the support point in. So you can save potentially a lot of operations by doing it this way. And you can also scale this way and things like that. You can scale back the largest vertex and have your scale also saved and all that kind of stuff. Yeah. One of the other benefits is also because this operates on support points, you can technically use this algorithm in a concave shape. So what would happen is if you have a concave shape, this algorithm just treats it as a cloud of points. It doesn't care about faces. I've seen a lot of algorithms that pass in faces. You don't have to do that. I don't know why they do that. You only have to pass in vertices. So it only treats it as a cloud of vertices. If you have a concave shape, it will pretend it's convex. And what that also means is if you have some velocity, right, all you have to do here is repeat this math, except every vertex is vertex plus velocity. Now you have a sweeping shape. So what this is basically doing, let me pull this up. 1 second. Microsoft Paint. Now you have a sweeping shape. So if this is my shape, I have this thing, and I am moving it in this direction, right? Then it's over here. If I just pass in both of these shapes to this algorithm, so I just check all the vertices twice, effectively GJK is automatically for me constructing this most maximal convex sweeping shape. So it's checking all the vertices of this shape. So if anything collides right here, it counts as a collision. And that is a pretty big benefit if you're trying to do some kind of continuous collision detection. So that's basically all I can think to add to the GJK algorithm. There are 2 different algorithms, and you can only really find one. But yeah, I'm going to put those links I talked about in the description, and I might also link to this code, which is on my GitHub. And also, I don't usually make videos like this. I don't know if I'm going to make more videos. Hopefully this helped. If I make more videos, I will probably make a video about time of impact collision detection. It's once you have this algorithm set up, it's very, very easy. And the other video might be about EPA, which is the expanding polytope algorithm, which builds on GJK to give you back the shortest possible vector to exit 2 overlapping convex polygons. So that might be what I do. Also, check out my game on Steam. It's in the bottom right of this stream. Yep, that's it. Hopefully this helped.